decreasing the current from the data. The n is a function of t at say t is equal to now 0 when we collect the data after 10 years or 20 years, what will happen? The function is continuous, so we find the per capita growth rate which is directly proportional to the part and also directly proportional to the date. And some people, just like here, some students come to here for study and absorb the services, and they will all other works migrated from one place to other. That is migration. In ecological modeling system, the forest department, forest department per area, they collected the species and number of species is there and they are counted. After 5 years, they also counted how many new trees are grown. The trees are grown, new trees are grown from they are either from the tree fruits or otherwise the migration is like the birds eat the fruits and come to one place to other and drop the seeds, and from these seeds the plant is grown. That is migration. Same type of in this model system is BNTP. Birth rate means BN minus death rate plus migration. Initially I not taken into account migration. That is E minus D is equal to N, that is Rn. If we differentiate this one, R, what is the meaning of R? R is birth rate minus death rate. That means growth rate. That is per capita growth rate, and you get a solution of the differential equation. Np is equal to N0 e to the power R. What will happen? We try to face portrait of this one. See, at t is equal to 0, that is a, this is time, and n is equal to t is equal to 0, and when r greater than 0, and when r is less than 0, then and r equal to 0. The following three cases may arise. What will happen if birth rate r less than 0 means birth rate is less than death rate, then the population will go to extinct. And r equal to 0 means the population is constant, and r greater than 0, population is exponentially grow. But in any population, t tends to infinity, does not goes to infinity. I'm sorry to say, only the human census data worldwide, the only population of the human population is grow rapidly and infinitely, but in any area population, they need resource like sunlight, food, area. So they are fight for each other. The changes, this model is known as Malthus model. Now, in a model system where t tends to infinity, when r greater than 0, population goes to infinity, they are fights for each other for space, food. So, what will happen? A PNDT is equal to RA minus A n into n. Why n into n is negative? If we fight each other, while our energy will loss, that's why the term will take it as negative. And what will happen? If we consider 1 minus n by a, what is a? A is equal to r by. This a is known as the carrying capacity. You know this one. And what will happen? If we solve the system in boundary equilibrium, we get equilibrium point. What is boundary equilibrium point? When P and dt is equal to 0 for any value of it, the point is known as stationary point or equilibrium point. And from this, we get equilibrium point is here, n is equal to 0 and n equal to k. If we solve this one, n equal to 0 is the unstable point and n equal to k is a stable point. What will happen? If this value n equal to k. When population is high, they go to the and if then use the point is sigma. This point line k is known as the carrying capacity, means the highest population at any time. It tends to infinite. Now we move to our model system. Now we go to the discrete system. Discrete system means we find here it tends to infinite. What will happen? P is equal to 1, P is equal to 2, P is equal to 3, 4, 5, 6, that's like this. That means with piecewise system we will take this system is known as discrete system. See, now from here, the mathematical biological modeling started from this point of view, and because the father of this model system, you know, the model is Lotka Volterra, that is written is here, Lotka Volterra model. How the model is reduced. The Lotka in Atlantic Ocean, go to the Atlantic Ocean and see, people are catching fish here, and in some year, they both fish and some year the fish is less. That is oscillatory in behavior. From this, he does the model PHPT is equal to alpha x. And partners here, they predate the fish, and that the population is called predator, dy/dt. What will happen? The predator, the fish, the growth rate of the fish population is decreases, that is minus beta x and y. And y dy/dt is minus gamma y. And in what? They consume the prey as the rate del xy. So what will happen if y is equal to 0, then what will happen? dx/dt is equal to alpha a. That is when this population is unbounded growth. But when we consider minus beta xy and this guy, and if x equal to 0, then dy/dt is equal to minus gamma. What will happen? The predator without food population goes to die out. Now, next. Now, we try to discretize the system, same system. See, A is equal to alpha x minus beta y, and dy/dt equal to minus gamma y plus delta x. Now, earlier I told that T is equal to, we consider T equal to 1, 2, 3, 4, 5 like that. That is discrete system. So using the piecewise constant argument for differential equation, we discretize the system and derive a discrete counterpart of the system described the following nonlinear difference equation. This is the first part of the nonlinear differential equation. 1 by dx dt as x n plus 1 and x considered as xn and y considered as yn is the this is the non-difference equation form. Next slide. Now we solve same method as continuous process continuous, but here is other is so to solve this problem, here is a trick. We consider here x n plus 1 is equal to x n e to the power alpha minus beta 1. When we solve this system to an equilibrium point, so we convert it to solve. We need to solve the following system in equation. Replace x n plus 1 and x n as x, y n plus 1 and y n as y, and we got the system in equation 3. From 3, we solve this one and we get 2 equilibrium point E0, 0, 0, each turn x. Next slide. Now, similarly, in continuous system, we also get E0, 0, 0, and another equilibrium state E extra x and y. Again, you must know that if we all try to find in the neighborhood of this point, equilibrium point 0, 0, in continuous system at the point E0, 0, 0 is the unstable point. And this term we get a center, just like it. If we base put it in our xy. Now, that means in continuous system, we find the system is center means the eigenvalue we get from the Jacobian matrix is purely imaginary and it is an oscillatory behavior. So we go to the see. Now we solve in the Jacobian matrix of the system of this model and try to find the local stability at each point. Go to the next slide. See, at E0, we find two eigenvalues. Lambda 1 is equal to e to the power alpha and lambda 2 is e to the power minus gamma. In model system, you know the exponential value alpha is greater than 0. We get value is always greater than 1. And another eigenvalue is e to the power minus 1. That means we get greater less than 1. Therefore, E0, 0, 0 is a saddle point. Next slide. At equilibrium point, interior recap from resistor, we to find the equilibrium point is stable or not. To find this, we use the star quant factor. What is the star criteria? The mod value of the eigenvalues, that is states J star mod minus 1 is less than determinant value of the eigenvalue if less than 1, if the system is stable, otherwise not. So we have to check the inequality mod trace J star minus 1 is less than J star less than 1. And what will we get? The trace value, trace means sum of the diagonal element. 1 plus 1 is equal to 2 and the determinant value is 1 plus alpha plus gamma y. See, what we get? Trace value is 2, means 2 minus 1. 2 minus 1 equal to 1, which is less than 1 plus alpha y less than 1. This inequality does not hold. That means the system is unstable, always unstable. Next. This is the base voltage of the system. You can never the system is stable, we get the oscillatory behavior. Now, we go to the next model as because, go to the next model. Next slide, yes. See, when you get a continuous population model, you get the oscillative behavior. If a population is increases, the pediatric increases, and the population increases. But when population increases, pediatric is decreases. This does not happen. That's because if we if oscillation is occur all the time, then the system is not exist. So try to modify this one. Modify from where this is modified. As the Lotka data is written as alpha x minus beta y. No, the x cannot be unloaded to go, and that's why the change is dx dt equal to rx into 1 minus k. And because as y tends to 0, the population goes to from the pay population goes to the carrying capacity, the highest population of the site. So we also modified the model, the continuous model, discretize the model. Next. See, we have to change this one, EXCT as xn plus 1, xn, and exponential of this value is equation number of 9. Now, we go to the find what will happen. See, to find the equilibrium point, we have to solve the system of equation at the point xn plus 1 and xn written as x, yn plus 1 written as a. We get G equilibrium point 1, E0, 0, 0, and the axial x-axis equilibrium, the axial equilibrium, E1, K0, and the interior equilibrium, E star, X star, Y star, the value of this. See, we need positivity of solution of the X star or Y star. So we get 1 minus gamma by delta by K. From there, we get K greater than this value. Next slide. Now, we go to the Jacobian of this system. And from the Jacobian of the system, part we try to find what will happen at E0, 0, 0. That is J E0. Next slide. We get the eigenvalue lambda 1 and lambda 2 is e to the power r and e to the power minus gamma. That is 1 is greater than 1 and less than 1. The term is E0 is always with certain point. Go to the next slide. And there is a BP here. We find the eigenvalue J1, E0 lambda 1. Where the value is get? The written is there. See, get lambda 1 is equal to r minus 1 and lambda 2 is x to the power minus gamma plus delta. So when the system will be stable, when two eigenvalues is less than 1, if that this value is less than 1 and this value is less than 1, then we say that the system is locally stable. R minus 1 is less than 1 is what is the range of R? 0 less than R less than 2. Get lambda value is less than 1. And second exponential value is e to the power minus this. So how can you get? If his value is negative, that is minus gamma plus delta k is less than 0. C means k less than gamma by delta. Then the system is stable. But to find out the interior equilibrium point, E star, X star, Y star, the condition is k greater than gamma by delta. That means if interior equilibrium point does not exist, then axial equilibrium point is stable. Go to the next slide. See. Now, the interior equilibrium point at J star, we get the value, we explicitly will not find the eigenvalue, so we use the star point criteria. Earlier I have S is mod of S value minus 1 is less than determinant value of the Icammwa matrix is less than 1 is satisfied if this is stable. From the above inequality, putting this value, we get the following inequality: 2r external minus by k minus 4 less than this value, then this system is stable. In continuous model system, you can also get the same result, but their external is less than k, then the system will be stable. Otherwise, this is unstable. So go to the next slide. This is the result of the system of equation and E1, P0, P0 approaches system here. Next slide. This is the result of that interior equilibrium. Any trajectory originally in the neighborhood of star approaches to star. That means if any point, initial point go to the stationary point, then the system is said to be stable. Next. Now, after a modified Rotka-Kortner model, you know the functional response as because mediator may be microbial level or invertebrate or vertebrate. Only introduce this one as we well learned as polling time 1, 2, 3, and now is 4 and 5 also. But if the predator is invertebrate, then the function is written as holding type 2 function. The predator functional response, and here the term C is the food conversion efficiency, as because the amount C never 1, as because if we consume any food, that all this food is not required for us, somewhere destroyed. So C always less than 1. And now this continuous system, we discretize the system to go to the next slide. Next. See, we try, you see that the model system has 6 parameters. So we non-dimensionalize the system. What is the dimensionless of the what is the procedure of dimensionless system? It is required to control our system, calculate and predict the nature of the system very easily if we dimensionalize the system, as because in earlier system you get, see earlier slide here, another first one, next one, no, next, next, go to the model, go to the last one. Upper. Go to the upper side. No, you go to the 31, change 30, reduce, decreases the numbers. 29, 38. Next slide. See, how many parameters are there? R, A, alpha, A, C. We try to dimensionless the system. What is the dimensionless? Here, see, E, A, N has a dimension population is either lakh or thousand or crores. T's time may be second, minutes, hour. So it has a dimension. What is the dimension of left side? The left hand side dimension is population per time. And left hand side and right side is when equal, when the dimension is same. So from here, we try to find the dimension of this parameter. See, dimension of A is population. See, the dimension N is divided by K. When they divide, then occur, division is occur if the dimension is same. That means the dimension of A is also the population. And so in first bracket we get 1 is a number scalar quantity. When you divided N by K, this is also a scalar quantity. Now you see in the outside the bracket, it is multiplied by R and N. N is population. That is the dimension of, what is the dimension of R? Is tiny. So left side is dimension and time inverse. First term is you get dimension and time inverse. C. A. Population. P also population. So we get upper side is population square. And what we'll get? P is population. And C. In lower side, this is 1 plus alpha HN. A is population. So, what will happen? H. We take H as a dimension of A is population inverse. And alpha is a scalar quantity. What will happen? No. See, this is 1 is written is here. So, what is the dimension of alpha? You have to find. So, you have to change this one. What will upper side? Alpha N. N is population, get population squared. But we need population per time. Now, what is the dimension of alpha? Dimension of alpha is population inverse and time inverse. As because we consider as population and time inverse, as because here is the number is 1 is a scalar quantity, so we get dimension per time. And here we get population square. How can it be reduced? Alpha is alpha HN means we get population inverse and population and time inverse. That means A is equal to time. We get the point of value and we from this we get the changes the model system. Go to next slide. Next. See, we put to consider the value of X and Y and we do non-dimensional the system. We get the equation number 50. You see, and earlier model the parameter is number of 6, but here parameters is only 3. So we can control and can say very easily either in the parametric region the system is stable or not. So if a more than 6, 7, 8, 9, 10, then we cannot specifically say the system is stable or not. Which parameter value is more sensitive we get. And if we non-dimensional this non-dimensional system, if we system is non-dimensional, the nature of the system cannot change. Or if we get any model and the non-dimensionalize the system, then system give the same result of the original one also. And now we try to solve the system. Go to the next slide. See, from the model system, we converted the piecewise constant argument of the differential equation, we get the following system of equation. Next. Following this system of equation, get three equilibrium point. One is 0, 0, and one axillary one E1, 0, and interior. Extra is AB by R minus B. So we need R greater than B, and Y star is A1 minus A2, and B star is visible. We get the following condition: A less than R minus B by B wholes. Now we Jacobian of the system 16. Go to the next slide. This is the Jacobian of the system 3. And we solve, we try to find the nature of the equilibrium point. Next slide. At E0, 0, 0, we get lambda 1 and lambda 2 greater than 1 and less than 1. E1 is 1, 0 is this value. And star point criteria, we get the stability condition of this value. Go to the next slide. This is the following result when E1 is stable. That is, interior does not exist. Next. If this condition is held, then it is unstable. Fixed point interior is stable, and these are trajectory of instant approaches to star. Next. Now, in appearance interaction, we first talk about the interaction. First, I've talked about appearance system. If two species are in same trophic level, they compete each other. So we consider a discrete model of competition model of two species for common resources. You know, this is the continuous model. Here, X and Y both are same population level, both are have a carrying capacity, and we get the following system dxdt is equal to this one. Here the parameter value A1 to A21 is the competition coefficient. Next, this is the discrete model system. See, very rich dynamics you get here. See, you get 4 equilibrium. E0, E1, two axial equilibrium. One is 1, 0 and 0, 1 and interior external. See, what is the value of external? We as because we have mathematics there, biological system is there. So either population dies out, neighbor population will be 0. So we must consider X star and Y star to greater than. We get if A1 to less than 1, then what will happen in the numerator? A1 to is less than 1, numerator is positive. A21 is less than 1, the numerator is positive. Then if A1 to A21 less than, the product term is always less than 1, so we get X star and Y star is positive. If we consider A1 to greater than 1 and A21 less than 1, we get one external value is greater than 0 and another one is less than 0. That means interior equilibrium point does not exist if the inequality change, one is greater or less. So if we get two interior 2 points which satisfy A1 to A21 less than 1 or A1 to A21 greater than 1. Next. Now, we try to solve the system to examine the neighbor with the local stability analysis. We get to find the Jacobian of this matrix. Next slide. The stability condition is written is here. Next. See. The following 4 cases may arise. First case 1, when the system is exists and condition hold, that means the species will coexist in future time. Next slide. If A1 to less than 1, A21 greater than 1, then X what will happen? Then interior equilibrium point does not exist. But axial equilibrium, E1 is stable and E2 is unstable. So we find the result. See, at the point x is 1, the system goes to that means if competition occur and competition coefficient is higher than A1 to greater than 1, A2 greater than 1, that means X dominates with Y and Y species will die out and intertypes the pay population will grows. Next, one case 3. When just opposite case. A1 to greater than 1 and A2 are greater than 1, then Y species dominate and X species dies out. See the point Y at the point 1, the trajectory goes to the point E2, 0, 1. Next slide. See. See, in continuous model system, we get there is a basin of attraction. That means we get to basin of attraction. From here, some trajectory goes to the point E1, 1, 0, and another one is E2, 0, 1, as because interior equilibrium point does not exist. The system will be unstable. We get a result at a point. What will happen? In continuous model system, we can find, see, this is the A population X, this is A population 1. To get E0, 0, 0, E1, 1, 0, E2, 0, 1, and E7. E0, 0, 0, you get saddle. If we consider initial point is here, this eastern is unstable, goes to the point, this will get to 5. If we initial point is here, if we initial point is here, we get this one is level. That is, from the considering the initial point, initial population type, and from this we get a separate line from between this line, the population goes either is E1 or E2 there. That is, we get two basin of actors. That's why I have written this form red and blue color. Next, these are references. If anyone is interested, go to the book of Irani, very good book. You can find this more application is there. Next. Thank you. Anyone have a question? For you, one was very good with the last person. Let's take a question. For me, online for serious model, the condition for gain value this time around. It's not just negative, it has to be negative, but it's what? I think that's a departure from what we used to have. Normally, we say the eigenvalue should be negative, but now, what did we see? That means we didn't, was it funny? Eigenvalues for stability, condition for stability, in this case, what he has taught us now. What did we see? It has to be what? Less than 1. It's not, that's, he presented it. He taught it. Is that not so? Yes, because you are talking exponential here. So it has to be less than 1. Okay, so there's a question. I was trying to just see if we actually following. So let me give the mind to answer. question.
Right. Thank you very much, Prof, for that wonderful enlightenment for me. So you were talking about the logical Volterra model indicators. So personally, I always want to look at every beginning from the end point. So um, if it was a malaria model now, for example, I could have known, oh, I'm trying to study maybe the predator, I'm trying to study maybe the population and all of those. But for this, I can't really say what are we trying to study in all of these things? What is the goal? What do you want to observe? So if you can help me throw light on that, I can see from the end point there.
Okay, so he's saying that for epidemiological models, maybe we are trying to study something around this, for this ecological model, right? So he wants to know what he will still do epidemiological model, but I think what's closer, he wants to know that okay, this is ecological model. So what are the possible things that we can derive from this ecological model as findings, important findings? What can we possibly say about ecology from the ecological model? Good. So Prof is going to give a paper in the next lecture for you to see. Okay, but Professor Bakari also want to say something? Yeah. Just now, I just introduced discrete models. You see, I just write the model and this model, continuous model system to discrete model. And in continuous models is the what will you find? First you find the stationary point and then make the Jacobian of this matrix from the Jacobian, from the eigenvalues. Nature, you can say either system is stable node, unstable node, saddle point, or oscillation area is there. That is the only I changes the continuous model system is a discrete model system part and done only local stability, no global stability is there. I in the next one I will say about the global stability analysis. Okay. Thank you so much. Did you get that? What we normally do with a continuous model, your local stability analysis, directly. So he just did the same thing with a discrete model. On that continuous model to
now is actually work with use some foundation of technology, which is the backbone of epidemiology. In mathematical ecology, the ecological concepts that are used in mathematical epidemiology, which so what we are doing with ecology is that we don't have much of ecologists in Nigeria. I don't know if there's any ecology because if you want to do ecology, you have to have a very strong background, even though they're in biology, they're in zoo or something like that. So they build the theory of population biology. And the theory of population biology is based on like data population. Data population is an ecological concept, but it's being used in epidemiology. You understand? So there are many then, so there are a lot of theories that have been built in ecology are being used in epidemiology. Answer questions. See? Because
okay, thank you so much. Let me get fine. Please let's appreciate our lecture now. Let me find out from the website anything we can next lecture. Okay. So just let's go down first. Samson.
Okay, so for that lecture, I think that was a very good introduction.